Hello and Assalamualaikum. Today, me and my friends Muhammad Aiman Faiz, Nik Muhammad Al-Amin and Nurhani Sofia will be talking about the application of determinants. My name is Amy Norain and I will talk about the introduction of application of determinants. What is linear algebra? Linear algebra is a mathematical discipline that focuses with vectors and matrices as well as vector spaces and linear transformations more broadly. Linear algebra, in contrast to other areas of mathematics that are frequently energized by new ideas and unsolved problems, is quite well understood. Its worth is derived from its numerous applications which range from mathematical physics to current algebra and coding theory. There are three types of representation of linear algebra, which is vector and vector spaces, linear transformation and matrices, and eigenvectors. The first representation of linear algebra is vector and vector spaces. Linear algebra starts with the study of vectors, which are defined as quantities with both magnitude and direction. Vectors are well suited to physical applications and are frequently expressed in terms of coordinates. Vectors can be represented as arrows in 2 or 3 dimensions as a starting point. However, linear algebra has been used in situations where this is no longer appropriate. In some forms of differential equations, for example, the sum of two solutions yields a third solution, and every constant multiple of a solution yields another solution. The solutions in such circumstances can be considered as vectors, and the set of solutions is a vector space in the following sense. Any two vectors in the vector space can be joined together to form another vector, and vectors so that can be multiplied by numbers to form shorter or longer vectors. Scalars were named because in the beginning they were just ordinary numbers that change the scale or length of a vector. Scalars are no longer ordinary real numbers in many recent applications of linear algebra, but the crucial thing is that they may be linked among themselves through addition, subtraction, multiplication, and division. Linear transformations are another way to represent linear algebra. Linear transformations are functions that translate or map one vector to another. Each vector is sent to C times itself in the simplest case of linear transformation, where C is a constant. As a result, all vectors continue in the same direction, but their lengths are multiplied by C. Another example is a rotation, which keeps all lengths the same but changes the vector directions. The term linear refers to how the transformation preserves vector addition and scalar multiplication. Linear transformations are viewed as matrices while doing computations. A matrix is a rectangular arrangement of scalars where two matrices can be added or multiplied. The product of two matrices represents the result of performing one transformation followed by another from right to left, and the result is usually different if the transformations are performed in reverse order. Thus, the product of two matrices relies on the order of multiplication if A and B are square matrices, which is matrices with the same number of rows and columns of the same size. Then AB and BA are rarely equal. The matrix for a given transformation is obtained using coordinates. The last representation of linear algebra is eigenvectors. Eigenvectors, also known as characteristic vectors, are highly useful in locating non-zero vectors whose direction is unaffected by the transformation. If V is an eigenvector for the linear transformation T, then TB will equal to lambda V for some scalar lambda. This scalar is known as an eigenvalue, and many practical applications focus heavily on the eigenvalue of the largest absolute value and its associated eigenvector. This is due to the fact that whatever process is represented by the linear transformation frequently acts repeatedly, feeding output from the previous transformation back into another transformation, resulting in every arbitrary vector converging on the eigenvector associated with the largest eigenvalue, though somewhat rescaled by the power of the eigenvalue. In other words, the system's long-term behavior is determined by its eigenvectors. Finding the eigenvectors and eigenvalues of a linear transformation is frequently done using matrix algebra, which was invented by the English mathematician Arthur Cayley in the mid-19th century. His work served as the foundation for our current linear algebra. Next, we will move on to what is application of determinants. A determinant is a scalar number that is a function of the square matrix entries. The determinant of a matrix is any square matrix that can be correlated with a real number. Matrices that do not have determinants are described as a non-square matrix. By determining the value of a matrix determinant, we can learn about numerous properties associated with that matrix. Determinants are useful for a variety of purposes, including determining eigenvalues, inverses of matrices, and solving systems of linear equations. Another way of determining the inverse of a matrix is to apply determinants such as the adjoint method. It also includes applying Cramer's rule, which can be used to discover the solution of linear system, although Cramer's rule can only be applied for systems with non-singular coefficient matrices. Simply by applying determinants, we may build the cofactor matrix and determine the adjoint of a matrix, find the inverse of a matrix using the adjoint method, and solve systems of linear equations using Cramer's rule. Next, I will explain about the purpose of study. The purpose of this case study is to study how this application of determinants can solve linear equation problems and how we can implement these determinants in real life. Additionally, the video will serve as a visual representation of how we apply determinants to solve linear equation problems, allowing our viewers and readers to immediately understand it. That is all from me today. Thank you.
Assalamualaikum and hi, my name is Nurhani Sofia binti Nur Jazman, and I'm going to proceed from what Amy has presented. So Amy stated that the purpose of our case study is to study how this application of determinants can solve a linear equation problems and how we can implement these determinants in our real life. So in order to do that, we have came up with a problem statement to prove that it really can be applied in our real life. First of all, let me be clear that our case study involves a vaccine business, or to be specific, matrices are involved and used to determine the price for each dose of different types of vaccine. Now let's get to the problem statement. So country A has received 3 different types of vaccines, which are Oxford AstraZeneca, Pfizer BioNTech, and Sinovac in April, May, and June. So for every month, 3 million doses has been received by this country A. And even the total price has also already concluded. As you can see, we have created a table so that people can see the information given clearly. So what's the problem here? Now let me ask you, do you wonder how much does it cost for each dose of vaccine? And can you find any information about the price for each dose of vaccines in the table? No, you can't. And that's the problem. The problem is we need to find the price for each dose of different types of vaccine. And Cramer's rule will be used to calculate the solution to this problem, which includes the application of determinants. Every single problem has a solution, no matter what method we use to solve it. So now I'm going to explain what kind of method we use to solve our problem. So like I mentioned before, we will be using Cramer's rule as a method to solve our problem. It's a very convenient way to solve a linear equation without having to solve the entire system. And it can actually be calculated quite quickly. As for instance, if you use any other method such as Gaussian elimination, the working will get too long and it might be complicated compared to if you use the Cramer's rule. So Cramer's rule, it provides the solution of a system of linear equations with n variables and n equations. And note that Cramer's rule is only applicable on square matrices that has non-zero determinants and has a unique solution. And now I'm gonna pass to Amin so that he can explain deeper about how we use this Cramer's rule to solve our problem just now.
Assalamualaikum and hi, my name is Nik Muhammad Al-Amin Wel Aziz. So I'm going to present about the problem solving of our problems, which is we need to find the price of each vaccine. Okay, for the first step, we need to list all the equations from the information given in the table from the problem statement. Then we can assume that each price of the vaccines represent as X, Y, and Z, which is X is AstraZeneca, Y Pfizer BioNTech, and Z is Sinovac. Since it is a huge number, we can simplify the equation by dividing all the numbers with 100,000, which is we can get as 5x plus 10y plus 15z equals to 419, 12x plus 5y plus 13z equal to 322.3, and 2x plus 20y plus 8z equals to 506.8. For the second step, we need to change the linear equations into metric form, which is metric 5, 10, 15, 12, 5, 13, 2, 28, we can assume as matrix A, and 419, 322.3, 506.8 as a constant matrix. For the third step, we need to find the determinant of A from the matrix A. So to find the determinant value, we can use Cramer rules. we can use or choose any column and row to find the determinant value. So for this case, I choose the first column and then I substitute the value and then I get determinant of A is equal to 1650. Step 4, we need to find the determinant of AX, AY and AZ. So to find AX, we need to replace the first column, which is represent X, with constant matrix. And then we can use Cramer rule to find the determinant of AX. Then we get 6600 as a value of determinant of AX. To find the value of determinant of AY, we need to replace the second column, which is represent Y, with constant matrix. And then we can use the Cramer rules to find the determinant of AY. So we get 32,175 as a value of AY, or the determinant of AY. To find the determinant of AZ, we need to replace the third column with constant matrix. And then we use the same method, which is Cramer rule, to find the value of determinant of AZ. And then we get 22,440 as a value of determinant of AZ. For the last step, after we find all the determinant values of A, AX, AY and AZ, we can calculate to find the price of one dose of each type of vaccine. Each variable represents the type of vaccine. X represents AstraZeneca, Y Pfizer-BioNTech and Z is Sinovac. To find X, which is the price of one dose of AstraZeneca vaccine, we can calculate as determinant of AX divided by determinant of A, which is 6,600 divided by 1,650, and we get $4. To find Y, which is the price of one dose of Pfizer-BioNTech vaccine, we can calculate as determinant of Y divided by determinant of A, which is 32,175 divided by 1,650, and we get $19.5. And the last one, Z, the price of one dose of Sinovac vaccine, we can calculate as determinant of Z divided by determinant of A, which is 22,440 divided 1,650, and we get $13.6. So we can conclude that the price of one dose of AstraZeneca vaccine is $4, Pfizer-BioNTech $19.5, and Sinovac is $13.6.
So, hi, Assalamualaikum. So, as for the conclusion after determine the result of price of each of the vaccine based on the brand. So, as for AstraZeneca is $4, Pfizer-BioNTech is $19.5, and Sinovac is $13.5. National Vaccine Authority in country A can determine on how many vaccine that they can buy the vaccine from different brand based on the budget that allocated. From this calculation also, they can make sure that there is no shortage or maybe fraud in the transaction because they can calculate the price based on this calculation. Also, they can determine the total of doses that they can receive based on the calculation. From this calculation, the authorities that was assigned for this job can save their time on the calculation of the price and also the total of vaccine that being used or purchased. Lastly, from the calculation, we know that determinant can calculate the price of each dose of different types of vaccine in country A. Determinant implementation can address the difficulty of linear equation on how we can apply those factors in real life. Thank you and Assalamualaikum.